Okay. Yeah. Great. All right. I just posted the video for the first five. Um, it's gonna render for a while, but it should be ready by about, I don't know. I don't know when. I'm not gonna even say a time, but it should be ready soon. Let's do more. Okay. So this should be six. Get rid of everybody that's not six. All right. So you're looking at a piecewise function this time, and the two pieces are a linear function and a quadratic function. That shouldn't worry you too much because hopefully by now you get it. You get that this linear guy, he's continuous on his entire domain, and his entire domain goes from negative infinity all the way to infinity. Now, he's only defined to go from 0 to infinity, but we can definitely say that f of x is continuous on 0 to infinity. Because again, on 0 to infinity, we're being defined by a linear function, which is a polynomial, which is continuous. So we know there's no issues for any values greater than 0. And the same for this quadratic. This quadratic is also a polynomial. It doesn't have any issues anywhere on its entire domain. So that means we're certainly good. Did I just do that backwards? Of course I did. Luckily for me, it doesn't really matter. But that first equation, the linear equation, says we're good for the x's less than 0. That's negative infinity up to 0. And the quadratic says we're good from 0 to infinity. So the only thing left to analyze is, are we continuous right at 0? And we can tell pretty fast that we just plug those in and see if we get the same answer, because if we get the same answer, then the left and right hand limits are equal. So plugging in 0, you get 0 minus 7 halves. So we can see that the limit as x approaches 0. Now which direction are we coming? This is less than 0, so we're coming from the left. But the limit from the left would be the negative 7 halves. And we can see that the limit from the other side, well, that's going to be given by the quadratic equation. So plugging in 0 gives 0 plus 0 minus 2. So we can see the two left and right hand limits are different. So that seems to imply a jump discontinuity. Now, I don't need to know this, but just because we do know it, it wouldn't kill us to say that the actual function value at 0, it's given by the one that has the underline, right? That says x can be 0. So it would come from the line, it would be the negative 7 halves. That's really completely irrelevant, and you don't need to say it, because as soon as you have two limits that are both exist and both are finite but they're different, we can now safely say that since these limits exist and are different, we'll say therefore f of x has a jump discontinuity at x equals 0. So how's about 7 now? 7's another rational function. My voice is pretty messed up, so I apologize if it sounds bad. But also I don't care if it sounds bad. Too bad for you guys. Where are we? I would factor this. We get negative x minus 4x plus 3. You guys should probably be reaching for the fast forward button, because this is now very, very much like one we already did. Those factors cancel, so I get a removable discontinuity. Who's this guy like? He's like this guy. Remember number 4? We factored, something canceled, so we ended up getting a line with a hole in it. Looking at this guy, we factored, something canceled. We're going to end up getting another line with another hole in it. You could distribute the negative in and get negative x plus 4. You could sketch that graph if you wanted. We're going to be on the y-axis at 4. But we're going to have a slope of negative 1, so we're going to come down. But over here at negative 3, we get a hole. So there'll be a hole there at negative 3, and then a line like this with a slope of negative 1, running. There's your picture. You can tell that thing is removable. you should be able to write me an argument by now that satisfies all of that stuff. So guess what? I'm not going to do it. I'm going to take a little time to myself and not explain that any further. Let's do 8. 8's looking pretty similar too, though, I gotta say. It's looking pretty similar. So looking at 8, first thing I would do is, you already know, I'd factor. So looking in the numerator, it does factor. It's an x minus 3 and an x plus 2. And yeah, we're going to be skipping this one. Because guess what? The x plus 2's cancel again. So clearly, again, f of x has removable discon. Remove discontinuity at x equals negative 2 because of the limits. The limits are going to be equal again. What are the limits? Maybe I shouldn't skip that. Maybe somebody missed the memo on this, but to find the actual limit, you can't plug negative 2 into the original. If you plug negative 2 into the original, you'll just get 0 over 0, which will be indeterminate. But you can plug into the simplified version. So if I plugged in negative 2 minus 3, that's going to tell me that both of my limits, the limit as we approach negative 2 from the left, is negative 5. And that's also the limit from the right. But then the function itself, the function of value at negative 2, is undefined. So we definitely have that locked down. We're saying the limit from the left does equal the limit from the right. They both equal negative 5, but the function value is not negative 5. The function value is undefined. Again, it's another line with a hole in it. Okay, moving on. So we're on to these. These are the ones where we officially have to justify our answers with limits. So I don't like this. Something's wrong with the aspect ratio here. I like this guy. We'll do 9, we'll do 10, 11, 12, 13. So what do I do? Duplicate once, duplicate twice, duplicate 3 times, 4 times, 5 times? Okay, so we're doing 9. Alright, the good news is this is not another line with a hole in it. The bad news is he seems real familiar. Where's the guy? Isn't that the same guy, number 5? Oh, it had a negative, but it's x squared over 2x plus 4. This guy's x squared over 2x plus 4 just with a negative in front? I'm not doing that. There's no way I'm doing that. All that does is flip the whole graph upside down. So since we already did 5, it would literally just be this same graph just flipped upside down. So all the same reasoning would still apply, except these limits would reverse. Suddenly my left-hand limit would go to positive infinity, and my right-hand limit would go to negative infinity. So there, pretend that number 5 is actually number 9. Let's do a little quick cosmetic surgery here. That actually says 9, and there's a negative in front. There's your answer. Sorry if it seems like I'm being lazy, but if I explained this, you guys would all fast forward through it anyway, because we literally talked about it already. So, no 9, not doing it. We can do 10 though. We can do 10 all day. 10. Okay, 10's good. 10 actually has a quadratic in the denominator, which we haven't really seen yet. The fact that the denominator is quadratic means we are going to end up with 2 discontinuities. And so even if I factor this, I get an x plus 1 over x minus 2x plus 1. Alright, so it's true. This thing cancels again, but it cancels differently from how the other ones were canceling. These do cancel, and I do get a new function. But notice there's still a discontinuity down in the denominator. There's still a discontinuity at 2. Since that guy didn't cancel, we know that f of x will have a vertical asymptote. And since the negative 1, the x plus 1 factors did cancel, that tells me that at x equals -1, we'll just get some kind of hole. So I could graph this for you again if you wanted me to. Essentially what you do is you just graph the graph of 1 over x minus 2, which hopefully you guys all know, would just shift to the right by 2. So your vertical asymptote is there now. And your horizontal asymptote is 0. That's here. And again, where would my branches fall? Well, if you plug in 0, you get -1/2. So if I'm negative at 0, then I'm negative everywhere. And then it never hurts to check. So if this is 2, then try plugging in 3. Well, 3 gives 1. That is above. So then my whole branch is above. So the only mistake left to fix is I actually showed a point at -1. We should actually have a hole there. And what is the y value there? Whatever the y value there is our limit, and we can find that y value by just substituting in here. And so we can see that at x equals -1, the y value that we get is -1/3. So these are the coordinates of the hole. So with a graph to look at, with the coordinates of the hole, analyzing this thing's continuity should be a piece of cake. We now can say for sure that f of x is continuous on the interval that goes from -∞ up to -1, and then it goes from -1 to my next discontinuity at 2, and then it goes from 2 to infinity. So those are all the places where we are continuous. Then we can say f of x has an infinite discontinuity at x equals 2 and a removable discontinuity at x equals -1. And that's it for your sort of text-based answer. Now just make sure that you're giving me a math-based answer using limits. And I'll kind of color code this, let's say. So why am I getting an infinite discontinuity at 2? Well, that's because the limit as x approaches 2 from the left of this function. Well, in our graph we can see as we approach from the left we go down to -∞. And the limit from the other side ain't much better. It's still going to be infinity. It's going to be positive infinity though. But that's pretty ironclad evidence that at 2 we're getting a vertical asymptote, which is an infinite discontinuity. Then red, orange, yellow, green, blue, purple? Let's do purple. All right. What about this removable discontinuity? Why do we know we have that? Well, again, to justify that, we need all three values. We know that the limit as x approaches -1 from the left of this function is the y value of the whole, -1/3. And we know that's the same exact limit if we approach from the other side. So we can just build this sort of extended equation and say x approaches -1 from the right hand side. So those are the same thing. And then of course we have to say, but the actual value of the function at -1 does not equal -1/3. It's undefined. Okay, so we're certainly not continuous, because if we were continuous, the limit would equal the limit, which would equal the function value. But we're getting the same limit. The limits are equal, but the function is something else. That implies a hole that's not getting filled anywhere else. That's a removable discontinuity. All right, that's 10, 11. 11 bringing anything new to the table? Gotta say, getting a little bored. No, 11 doesn't bring anything new. Well, it kind of does. Yeah, fine, 11. All right, 11. 11's another rational function. And rational functions get their discontinuities from the denominator being equal to 0. Now this denominator, it's not factorable, so the only way to find the zeros then would be to use the quadratic formula, which is this. But before I knocked myself out trying to actually do all this math, remember the b squared minus 4ac part is called the discriminant. And if it comes out positive, then I can take the square root of a positive and I'll get a real number. It just might be ugly. And so then I would expect that I do have two zeros. They're just irrational, and both of them would be vertical asymptotes. But imagine if b squared minus 4ac was negative. Then you'll try to take the square root of a negative, and then your two solutions, your two zeros, will be non-real, which means they have no effect on the graph if they're non-real. And then the graph would have no discontinuities. And that's what happens, because b in this equation, in our denominator of course, b is 1. And 1 squared minus 4, take away a, which is 1, times c, which is 1, is giving me 1 take away 4, that's negative 3. And again, up here in the quadratic formula, I'm now trying to do the square root of negative 3, which gives me a big old imaginary value. So both of my solutions are now complex. Or sometimes instead of that, we just prefer to say they are non-real. That means the denominator here never really equals 0. So f of x would be continuous on negative infinity to infinity. And I think here, if you just kind of said we're continuous on that entire interval because the denom has no real zeros. And if obviously if you have all this math over here too justifying it, then this answer is great. You'll tell me that we're continuous on this entire interval because the denominator has no real zeros. I guess we should probably also say it has no discontinuities. But that's kind of implied. Exclamation point. All right, moving on to 12. 12 is that guy. He doesn't look so tough. Yeah, okay, whatever. Obviously there's a problem at 1, right? Because 1 is going to cause division by 0. But there's no real problems anywhere else. Looking at this guy, again, I could sketch the graph if I truly felt like it. 1 is going to be a vertical asymptote for us. The other asymptote would be a slant asymptote, and with a negative, that implies a negative slope. So I don't know where it goes, but maybe it comes down like this. Anyway, what next? Imagining if I was just slightly greater than 1, just slightly greater, I would get a positive thing over something just slightly greater than 1. Take away 1 is a positive, but then there's a negative in front of it. So my positive over positive would actually be a negative. And if I'm just a little bit bigger than 1, then I'm dividing by a decimal, which makes the whole thing big. So I'm getting a big negative number. That tells me I'm coming up this asymptote, turning and heading back down. Okay, what if I was just a hair less than 1? Yeah, like if I was at like 0.9, then I'm still going to have a negative out in front. This number squared is still positive. In the denominator, though, I'm getting a negative. So that's going to end up giving me a positive. An overall positive that is large. So I would be up here, and I'd be coming down that asymptote, turning, following the other one. So that's a very, very, very rough sketch of what this is. But it definitely gives me an idea of the behavior on either side of 1. And it gives me an idea of the end behavior, too, in case I chose to ask you about the limit of f of x as x goes to infinity. If I asked you that, we can see that for sure as we go to infinity, the function goes to negative infinity. Okay, but no one cares about that. We're just doing continuity. And again, we can say that we're continuous on the interval that goes from negative infinity all the way to infinity, with the exception of the vertical asymptote. So again, it's the same old thing. Continuous on negative infinity to 1 and 1 to infinity. And then f of x has an infinite discontinuity. At x equals 1. And again, to justify that, just tell me how the two limits exist, and at least one of them is infinity. So it has because the limit as x approaches 1 from the left is something, and the limit as x approaches 1 from the right is something. All right, again, we graphed it. You don't really need a graph, but you do need to kind of think it through like I did. Just thinking about, hey, is it a positive over a negative, or is it a positive over a positive? And you can kind of just puzzle out, am I a large positive value or a very small negative value? And you can figure out the behavior. But looking at our graph, we can see that the limit from the left, for sure, has us going off to positive infinity, while the limit from the right has us plummeting down to negative infinity. But just citing those two limits and showing that even just one of them is infinity, that proves we're in infinite discontinuity. So that's it. Let's do 13. And I did 13 in class for somebody at least. This guy's a little different, I guess. For this guy, I shouldn't need to factor anything. Yeah, my dog's trying to fit in on my dirty bed. Oh, he gave up. Okay. Goodbye, dog. Alright, what is this? Again, it says here x cannot be 0, and it says here x must be 0. What does that mean for the graph? It means that I would expect to see, at least everywhere that is not 0, I would expect to see the graph of this parabola. What's that guy look like, by the way? Well, he is factorable. Isn't it x minus 3 and x minus 1? That tells me that at 1 there's an x-intercept, and at 3 there's an x-intercept, and the positive leading coefficient tells me that I open up. Oh man, that's the worst. That's a very badly drawn parabola, but I don't care. Alright, great, I did it. It opens up like this. And guess what? I can't be 0. So right there's actually a hole. So the only question is, hey, at 0 the function is 3. So does that mean 3 is here? Or is 3, rats. Or is 3 up here? Maybe this is 3. Ooh, but wait, maybe this is 3. Because if the hole has a y value of 3, then the function being 3 would basically fill that hole right back in, and we would go from having a removable discontinuity just back to being continuous. But if that hole is at 5, then 3 is down here. Now you got a removable discontinuity. Or if this hole is at 1, then 3 would be up here. We're back to having a removable discontinuity. So it seems like to decide whether our discontinuity is removable or whether we don't have a discontinuity at all, it sounds like we need to check out the behavior of this quadratic, see what its y value is. And as we plug in to this, by the way, what are we finding? We're literally finding the limit as x approaches 0 from the left. Which, by the way, will also be the limit as we approach from the right. Both of which are things we need anyway. Okay, so again, how do I evaluate? You just plug in. You plug in 0 and oh my god, I get 3? So this hole really is right at 3? But then the other part of the piecewise function says that at 0 we get 3 anyway? That means the proper placement of this point is right there. The whole graph is actually symmetric, not symmetrical, but the whole graph is continuous again. So here we need to just say f of x is continuous on. Negative infinity to infinity. There is no discontinuity at x equals 0. Like many of you probably assumed there was, but there isn't, because the limit as x approaches 0. Maybe this is the rare time to go ahead and use a biconditional. So the limit from both directions is 3, and the value of the function is also 3. So that's it. That kind of justifies everything. That would be a good answer to a question like that. That was 13. There is no 14. Does that mean I can throw in the towel finally? Yeah, alright. So there is this. I thought this was worth talking about too. This can be something. So this was in the thing. Let me just show you, I guess. So this was in, where did I put it? I put it in an announcement. There's an extra practice thing. Extra practice for quiz 3. A blank copy. Let me just download it. Then what I can do is come back here. Yeah, we're back. And I can say file import. PDF. Okay, I'm back. I found it. Anyway, it's this document here. It looks like crud as I imported it. Yeah, it's got all this scraggly stuff. But, you know, it's just more problems. And so you guys could work on these if you wanted to. It's got these three-part piecewise functions. So you'd have to consider the continuity at -1, and you'd have to consider the continuity at 2. So sort of two different points that might be discontinuous. You also have maybe some more interesting functions built in, and I do expect you to know this. So something like a 3 to the x, that's an exponential function. You should be able to handle that. All that's relevant here is if I plugged in 2, wouldn't 3 squared just be 9? And if I plugged in 2 here, 2 squared is 4, minus 1 is 3. That certainly implies here that at 2, are we continuous? No, that's wrong. There's a jump discontinuity there. What about at -1? -1 gives positive a third. And if I plug -1 in here, 3 to the -1, that just takes the reciprocal of the base. That's positive a third, again. So are we continuous here? Yes, that's true. So these are some good questions you could think about. Natural log is built in here. That's something you should probably know a little bit about. This guy's pretty normal looking. Sine, cosine, and tangent. Probably won't ask about that, but you never know. Anyway, this question at the end, the one that's supposed to be test prep or whatever, I thought this was worth talking about. So let's go do that. Alright, so what's happening here? There's no function rule for you. There's nothing to go off of. It's broken down to strictly the stuff that matters. What is this? We're approaching the b value from the left-hand side. This is the left-hand limit. What's this? This is the right-hand limit. And what's this? This is the actual function value. And those three things are all we ever need to classify any discontinuity. So this is asking us, hey, are we continuous at 1? Well, here's 1. And it says here that the two limits are different. The function value might equal this, but the limit is different. So are we continuous? No. Now we can do better than that. We know that because the two limits are different, but finite, what kind of discontinuity is this? I'll wait. I'll wait for it. Pause the video and think. What is it? It's a jump. Right? Alright, what about the next one? Are we continuous at 2? Let's see. We get a 5 and a 5. That's cool and all, but then the function isn't a 5, so no. What kind of discontinuity is implied when the left and right hand limits are equal, but the function value is somewhere else? Pause the video. Think. Try to get an answer. It's removable. Okay, great. What about a 3? I mean, this one's kind of dumb. It's 1 and it's 1 and it's 1. So are we continuous at 3? Yes. Okay. Oh, sorry. I thought this was multiple questions, but it's actually just a multiple choice. So which of the following must be true? The fact that we're continuous here. So the answer was C. But you can see how this might be interesting to actually just treat all of these as separate questions, right? What do you know is happening at 1? Well, I can tell from the limits that I'm getting a jump discontinuity. What's happening at 2? I'm getting removable discontinuity. What's happening at 3? I'm continuous. And then obviously if this guy happened to be infinity, then we could say that at 3 we're getting an infinite discontinuity. But this is a nice, really simple way to just think about all possible discontinuities with the sort of least amount of information given. No graph, no functions, but you still have all the information you need. Anyway, it's like 9:50, so let's get this second video up, and hopefully those of you who are still awake can benefit from it. Okay, goodbye. See you tomorrow.